Welcome to Oddly Real. I'm Nem Stefanovic. What we experience in our everyday world is based on well-known expected behaviors. For example, if we throw a baseball at a wall, our experience tells us that we could trace its entire path up to its point of impact. It would be strange if the baseball instead traveled like an amorphous wave, spreading across a wide range of space, and then materializing into a random, unexpected location on the wall. Or imagine if we threw a series of pitches, one baseball at a time, through a broken fence with a few openings in it. Our intuition would tell us that the ball would go through an opening in the fence and hit a spot on the wall along its trajectory. It would be very odd if the baseball never, under any circumstances, landed within certain regions of the wall, even though they were clearly in its path. Now imagine if you closed up some of the holes in the fence, but now your pitches through the open holes are landing in the spots on the wall that were previously never hit before. As bizarre as all of this might sound, this is in fact an analogous description of how our universe works. It is nothing like we are used to seeing, yet this is the true behavior of matter and energy at subatomic scales. In this episode, we'll describe some famous problems that could only be solved by applying the rules of quantum mechanics. These problems served as the basis to build up the laws of quantum mechanics. We'll also build an intuition to understand the true quantum mechanical behavior of light, energy, and matter, which is unlike anything we're used to. Throughout history, there have been significant divides among scientists about the underlying nature of both matter and light. For thousands of years, it was not known if matter was continuous, made of materials that could be sliced into smaller pieces without any limit, or if it was made of discrete, indivisible pieces called atoms. It was only in the past 200 years or so that there has been general agreement that matter is indeed composed of atoms. This started to become apparent when the budding field of chemistry started demonstrating that there were clear proportionality rules between products and reactants that strongly suggested an underlying atomic structure of matter. In fact, even atoms themselves are not indivisible, but composed of even more fundamental particles like electrons. A similar divide occurred when trying to understand the nature of light. For hundreds of years, it was not known if light was composed of tiny particles, each one representing a different color in the light spectrum, or if light was instead a wave propagating through a medium with its frequency of oscillation representing the colors. This disagreement appeared to be resolved about 200 years ago when Thomas Young conducted an experiment to split light across two paths called the double slit experiment, which resulted in interference patterns on a display. These patterns could not have been generated if light was made of particles. It seemed like there were finally some clear answers to some of the oldest questions posed to science about light and matter. But of course, the story doesn't end here. And in fact, it gets way weirder. Fast forward to the early 20th century. There were some gaps in our understanding of the world. One such gap was the famous Blackbody radiation problem. A blackbody is an object that is able to absorb light across the electromagnetic spectrum very well. Interestingly, they are also really good at emitting the entire electromagnetic spectrum when heated. Blackbodies radiate in the same way for a given temperature. However, classical physics, before quantum mechanics, predicted much larger amounts of ultraviolet high-energy radiation emissions than were actually detected in experiments. The theory suggested that light, which was believed to be a continuous wave, could carry any amount of energy. In order to explain the experimental discrepancy, Max Planck proposed a radical new idea that light energy was not continuous, but quantized, meaning only discrete chunks of light energy called quanta could actually be emitted. The quanta of energy had a formula. E is equal to h times F, where E is energy, F is the frequency of the light, and h was a whole new constant called Planck's constant. Thus, higher energy light, like ultraviolet light, needs more energy to be created, meaning it is harder to create, so less of it is emitted. Another famous phenomenon that laid the foundation for quantum mechanics is the photoelectric effect. Imagine a pure metal surface that is highly polished to remove impurities like oxides, and you put it in a vacuum. When light shines on the surface, electrons are emitted. The number of electrons and their energies are measurable. However, there was a mystery. Light, if it was a wave, would be more energetic if it was made brighter. Yet, when brighter light shines on the surface, it results in more emitted electrons, but they are not more energetic. They have similar speeds. The expected result was that the electrons would be more energetic for brighter light. Once again, a quantum solution was proposed, but this time by Albert Einstein. He proposed Planck's quantized energy description of light, E equals hf, could explain the observations. In fact, he proposed that one photon of light was responsible for each emitted electron. It was the frequency of the light which was responsible for providing enough energy to liberate the electron out of the material. More of this high frequency energy meant more energetic electrons. A brighter light would just mean that there were more photons, not more energy per photon. This actually fits with the description that light is actually particle-like, not wave-like. Finally, there was also a problem in explaining how heat capacities worked for different elemental substances. Heat capacity is a property of materials that relates the amount of heat energy required to raise the temperature of the object by 1 degree Celsius. Higher heat capacity means you need more energy to raise the temperature versus a lower heat capacity where you'd need less energy. It was expected that the heat capacity for elements should be similar if the number of atoms were the same. The rationale was that heavier elements would vibrate slower, given some energy, as compared to materials with lighter elements, which would vibrate faster. It shouldn't matter what the energy was, both materials should vibrate to some extent. However, this does not happen, and heat capacities drop with lower temperatures. Once again, this phenomenon can be explained using the idea that energy is quantized according to E equals hf. This particular case is fascinating since the energy of atomic vibrations relates to matter, not light. Yet once again, we see a situation where there needs to be enough energy in order for an atom to absorb a quantity of energy to start vibrating. If there isn't enough energy, the atoms won't vibrate, and hence, the heat capacity is reduced. In other words, you need a minimum quantum of energy for absorption. Energy does not get absorbed for smaller ranges of values as once thought. Let's reconcile the implications for these major problems and their solutions using quantum theory. Clearly, energy is both absorbed and emitted in discrete chunks, or quanta. We saw light emissions from Blackbody radiation required more energy in order to emit higher frequency light quanta like UV light. The photoelectric effect also confirmed that individual photons of light were responsible for individual electron emissions, and the energy of the photon imparted was responsible for the energy of the electron. Finally, we saw that quantized energy also applied to the vibrational motion of matter to explain heat capacity. Atoms needed a minimum heat energy to be able to vibrate. The totality of these results suggest a conundrum. We know that light was proven to be a wave from Young's two-slit experiment. Yet, the photoelectric effect clearly proves that light is made of particles, which are individually responsible for electron emissions. As strange as it sounds, all of these results are correct. Somehow, light behaves both as a wave and a particle. We have a name for this strange behavior. It's called wave-particle duality. The hard part is trying to reconcile this apparent contradiction. In fact, it's not so much that it's a contradiction, we're just completely unfamiliar with this behavior in our everyday lives. Luckily, there is a simplified way to think about this. We can say that light travels as waves, but light interacts as discrete particles. In fact, even weirder still, it turns out that it's not just light that behaves like this, it's how matter behaves as well. For example, electrons, which are particles of matter, can be fired into crystals, where the atomic arrangements of the crystal acts much like the two slits in the two-slit experiment for light. The result is that electrons experience both constructive and destructive interference. Thus, they only pass through the crystal in certain directions and not in others, which is confirmed by theory. The more massive the particle, the higher its frequency, hence the shorter its wavelength, and the more difficult it becomes to conduct interference experiments. Yet, in modern times, the interference experiment has been successfully demonstrated not only for heavier particles like neutrons, but also for entire molecules. Perhaps the strangest part of wave-particle duality is the wave part. What exactly is the wave? How does a particle act as a wave when clearly the particle has a particular location and an observable influence? What we know is this particular wave is spread out over space, and it describes the probability of finding the particle somewhere. For example, it is possible to use an extremely dim light source to conduct the two-slit experiment. The light source can be so dim that it's actually only emitting one photon at a time. This can be detected at the screen as a single photon hit. If you look at the location of any individual photon strike, it appears random. Yet, when you run the experiment continuously, emitting one photon at a time over a long period of time, you see the interference pattern. This is actually an amazing result, since we would expect one photon to go either through one slit or the other. How can there be any interference? There's no other light present, so what is the source of the interference? Is the photon interfering with itself? This is the heart of the nature of quantum mechanics and how particles behave. They truly act as waves until they interact with other matter. The particle wave spreads through space, going through both slits, with the interference pattern determining where on the screen the particle is allowed to hit. Notice that a well-defined deterministic particle could not experience interference like this. We are not saying that there is simply uncertainty with the position of a particle as it travels. What we are saying is that the particle is in some kind of actual wave-like state before it impacts the screen. At impact, the particle then acts like a typical single particle with a known position. This is really unlike anything we're used to seeing. Quantum mechanics gives us a way to predict the likelihood of how the wave nature of particles behave. This is called the Born rule. The rule states that the intensity of the wave at a point gives the probability of finding the particle at that point. The intensity of a wave is proportional to the square of its amplitude, which is the height of the wave. The intensity of the wave also describes the amount of energy of the wave. Quantum theory can't give us an exact position for the particle. It's truly random. However, it does tell us what the probability is for finding a particle somewhere as part of its wave description. I hope you were able to appreciate some of the remarkable results of quantum mechanics that came out of these examples. For millennia, humans have debated the nature of light and matter, whether it was continuous like a wave or discrete like a particle, only to find out that they're actually both. We don't really have an analogous experience in our lives to compare to this strange behavior, so it's hard for us to comprehend. Additionally, there is an underlying randomized behavior to all of this. We never know where a particle will be until after it has interacted with something else. For some people, this might seem a bit disconcerting since it sounds like nature isn't well defined. I'll leave you with one last thought that might actually make quantum nature a more appealing result. For intelligent, conscious beings such as ourselves, we want to know that we have free will and that we can make decisions and take actions independent of fate or a predetermined destiny. If the classical laws of physics before quantum mechanics held true, then every particle in the universe would have a definitive position and would be acting and reacting according to well-defined deterministic rules. So every action and event from the past into the future would have been predetermined. There would be no free will, and every event in the universe would unfold in only one possible way. Yet this is not the case according to quantum mechanics. There is an underpinning of randomness to everything in the universe, and nothing is perfectly predictable. If there was any possibility of free will for human beings, then the capacity for randomness would be one necessary ingredient. I hope you enjoyed this episode. Remember, oddly real, really interesting.